basically for body plot we have some specifications. This fresh reminder, as we have some specification in the time domain. So in frequency domain, and in particularly we are talking about body plot, because frequency representation, it could be other type of plot. You have Nyquist, you have other type, Nicholas plot, but here we're focusing on body plot because that's the one we use usually for design controller. It's the most well used method to design controller later on. That's why we focus in frequency analysis on body plot representation. So we have four main characteristics, as we have characteristics for time domain, settling time, overshoot, etc. So one is the gain crossover frequency, and how we define the gain crossover frequency is the gain at 0 decibel. So simply you go 0 decibel and you see the frequency of your curve at it. So if I go here like this, so my frequency is here, like somehow this is 1, 2, 3, somehow 4. Okay, so this is the gain crossover frequency. Gain crossover frequency, it's the frequency at 0 decibel. Phase crossover frequency is the frequency at minus 180 degree. So like here, if this is 4, 5, 6, around 6. So you see this 6, this 4. Let's look at them actually here in MATLAB, like somehow, okay. And here is 4, 3.6, let's say 4, 5.5, let's say it's 6. Okay. So those are the frequency. Also MATLAB, they give them to you. Third characteristic is the gain margin. And also how we learn the gain margin, how to find the gain margin. Remember from last time. So we said to find the gain margin, you need to go at minus 180 and go up and count, take this distance from here to here in decibel, and this will be your gain margin. Okay, that's the gain margin. You take the gain margin from minus 180. So the phase margin, you take it from 0 decibel. So you go to 0 decibel and you count how far you are from minus 180 and you determine the phase margin. So those are the characteristics. You should be able, as you're able to find the settling time, peak time, overshoot, so on. This is the same. These 4 points are very important. So the frequency basically, so 0.2, 3, 4, just like overshoot if you wish, phase margin and gain margin, like you see here. Those are very important criteria. 1, 2, 3, 4. Okay, so you need to be able to find them if I give you a body plot. Okay. So also last time I was talking about the damping frequency, damping ratio, sorry, and the damping ratio, how it affects the body plot. So we take omega equal 1 radian per second, so we don't change our omega. This is second order system, so I don't want to re-explain it. So then what's the difference between the omega which 1 radian per second and the omega which is going from 0 to infinity? Information. Okay, so this is a second order system, and second order system having this form is 2 plus 2 zeta omega plus omega s plus omega square. So I'm taking omega equal 1 and I'm varying zeta. So that's my system, that's zeta, I'm taking 3 value for z, and each time I'm drawing, that's my system. And what I'm doing for on my system, so my system has 3 z, z1, z2, z3, okay, z1, z2, z3, and for each time, for each system, so I have 3 systems, and for each system I'm putting it in a frequency analyzer where I'm injecting an input sinusoid frequency with a varying frequency within a frequency band, let's say from 0 to 500 hertz, and I'm looking to the output, how the output will behave for different frequency, and I'm recording. That's a frequency analyzer. That's what I'm recording, the Bode plot, which basically the ratio of amplitude between the output and input, which that's what we call the magnitude. So I'm drawing it for each and every frequency, and I'm drawing the phase lag between the output and input for the given system, and I'm getting it this way. So the omega here is the omega of the system, but omega here is the omega of your input. Clear? You remember it now?
Yes.
Okay.
Yes.
Alright, so yeah, and in the second plot here to your right, we are taking zeta for the system constant, and we are varying omega, and same we're putting it in the frequency analyzer, and we're drawing the Bode plot. You can see the effect of increasing the damping ratio, decreasing the damping ratio. Lower damping ratio, it will give you higher amplitude. Okay, and the system itself has a natural frequency of 1. So S2 plus 2 zeta S plus 1. So it has a natural frequency of 1. So when I inject a system, when I inject an input has a frequency of 1. If my input has a frequency of 1 equal to the frequency of my system, what should you expect? You should expect high amplitude in general. Why? Because this is, you are exciting your system at the natural frequency of the system. So that's why when the army walk on the bridge so they apply a frequency equal to the frequency of the bridge, they risk to break the bridge, because the bridge will vibrate a lot. So the bridge has high vibration at the natural frequency. So when you apply the natural frequency at your input, when you apply to the system the natural frequency of the system, which is 1, so you will get the maximum amplitude. That's why this is, as I told you from last time, here is the 1, the 10 to the power 0. Okay, which is here 10 to the power 0, 1. Here they do it correctly. Okay, now in the next step they moved omega, and see omega, when they moved it, they shift the Bode plot to the right. That's the effect of increasing omega on the system, and that's the effect of increasing zeta to the system. If a system with higher zeta, then you will have higher peak amplitude, because the damping, less damping, so you have more amplitude. And when you increase omega, it affects the frequency, the peak frequency. This we call it crossover frequency. When the natural frequency of the system increase, so the peak will be at the natural frequency. So the peak always at the natural frequency. So like here is 20, so should have here 20. Okay, here is 10, so I should have here 10. So here is yeah, here is 10. Here should be 20. Alright, any question? Any question about the natural frequency, the damping of the system, and how they affect the body plot? Stay clear?
No.
System stability. How we determine the system stability of a closed loop system? Actually, by using body plot, we can determine the stability of unity feedback closed loop system by looking at the body plot of the open loop system. Later we will see it, but here what constitutes a stable system? Basically, here is wrong, but I don't want to change the slide. So, as to you look to the phase and the gain margin. If they are positive, then your system is stable. Okay, that's basically the definition. How to know if the system is stable or not? By looking to the body plot. In time domain, by looking to the plot, I can understand that this system is unstable, or this system is unstable. And in body plot, how can I know the stability? By looking to the phase and gain margin. If they are positive, then the system is stable. So larger gain margin means the system can withstand greater changes, like more tolerant to disturbances. Larger phase margin, it reflects the system is tolerant to time delays. If you have time delay in the system, then the system is tolerant to time delay if you have large phase margin. Okay, and what's time delay? Disturbance, we know it, but time delay, what's time delay? Like, for example, I apply a step and then my system will start responding maybe after this delay. In practice, you have some system like this, so they need some delay to. Then if you have larger phase margin, and this is in general undesirable and lead to unstable system if it is big delay. So then if you have larger phase margin, your system is tolerant to time delay. So that's how it's explained. So let's see example about stability. Like we said, gain margin and phase margin, if they are positive, then system is stable. So I give you this system. So I tell you, is it stable or not? So this is the second exercise. First exercise maybe determine the specification in the body plot. So I give you second exercise. I ask in the exam, find if the system is stable or not. Of course, I don't give you the result on MATLAB. So I just give you the body plot. Tell me if it's stable or not. Okay, I'm taking the system with k equal 50, and I'm giving you the drawing for it, the body plot for it. So what you need to do, you need to go from 0 decibel up to and find the phase margin. We say the phase margin. How do you determine the phase margin? By looking to by taking it from 0 decibel, and this is the phase margin, right? If it is positive, then we are and if the gain margin also is positive, that means the system is stable. Let's find the gain margin. Gain margin, how to find? We find the gain margin by looking at minus 80, 180, and going up to when it crosses the body plot, and we go up to 0. And this is my gain margin. So, as I told you maybe last time, so if we are below the 0 decibel, then my system is stable. That's by definition. So we don't want to see there is some derivation for it, but now it's not responsible for. If we are below 0 decibel, means your gain margin is positive. So you count the distance from here to here. And the distance from here to here, it's 13.3 decibel. Alright, at this specific frequency. Phase margin, if you are above the minus 180, means you are positive. If you are below, means you are negative. So I'm above the 180, So also I count the degree from here to here. It is 101 degree. Alright, so then means the system is stable. You tell me system is stable because my gain margin is above the my gain margin is below the 0 decibel, and my phase margin is above the minus 180 degree. So you don't need to determine them exactly how much it is, because I'm asking just about the stability. But we know they are positive because above and below minus 180, so then system is stable. Also, you could check here, they put for you on this slide the time response. Actually, you look, it's nice and stable, so it's stabilized, so it's a stable system. So now we can know if it is stable by looking to the frequency domain. Okay, I increased my K. Actually, I'm using same system, but just I put it K of 230. So now I draw the body plot for it and ask you, is the system stable or not? So you will do the same. From 0 decibel, you go to find the gain, the phase margin. You find the phase margin, actually it is 0. From minus 180, you go and find the gain margin. You find the gain margin is 0. Also MATLAB, they give them to you as 0. So then you will tell me the system has a gain margin of 0, and told you if it's positive means you are, if they are positive means you are stable, if they are negative means you are unstable. So then if they are 0, like just you are at the marginally stable system, neutral stable system. So then in this case,
نقل
yes,
هلا هون معناتها إذا زدنا مثلا الكي زدناها شي 335 حيصير السيستم unstable لأنه هون الجين at zero صارت الجين
we will
margin at
see in the
zero.
next slide. We'll see it in the next slide. But yeah, it's good analysis. I like what you are analyzing. But look to the step response now. It is marginally stable. It's kind of the system where zeta equals 0 at the imaginary axis. So no damping and keep this way, oscillating to the infinity. So now, as your colleague Abdulrahman, right?
Abdurrahim.
Abdulrahim.
Yes.
As your colleague said, now if I take k, increase k a little bit, I'm keeping the same system, but I put my k equal more than 230, like 500 for example. And now I draw the body plot for that system. Okay, I look for the phase margin from 0 decibel. I go and find the phase margin, and this is my phase margin. I am below the minus 180, so then it is negative. So then directly tell me it's unstable system. But if you wish, you can continue and check the gain margin. It's enough to have one negative. But let's see the gain margin. In this example, the gain margin is also above the 0 decibel, so it's negative. Whatever value, good trained on how to find the value if you wish. But it's easy, just you find them from the curve. Remember, this is a logarithmic scale. So this is 10, then this is 20, this is 30, 40, 50, 60, 70, 80, 90, 100. So logarithmic scale. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. This is 0 0.1, 0 0.2, 0 0.3, 0 0.4, 5, 6, 7, 8, 0 0.9, 1. Okay, logarithmic scale. And you look to the step response, it is unstable system. Okay, so now we know how to find the stability for a body plot. Alright, any question regarding how do we find the stability using the body plot itself? Is it clear?
Yeah, it's clear.
Okay. As I told you, your frequency response is not only about body plot. Like in this few slides, we'll just try to connect the techniques we used in time domain advantage and convenient, why you want to actually work and why you are interested to work in frequency domain, which I was saying them in previous session, but we don't have a support slide. I just saying them. Using frequency response information, displaying frequency response information, and this is introduction to frequency response in general, not in particularly about body plot. Frequency response in general, as we are doing time domain response, time response, here is frequency response. So you know, we have determined previously the time response of linear system to arbitrary inputs and initial conditions. Well, arbitrary inputs, let's say, was looking to 3 type of inputs: step, ramp, and parabolic inputs. Okay, so this is something we know the time response, and that's how the time response look like usually in function of time, response function of time. And we studied the characteristic of certain standard systems to certain simple inputs. Basically, simple inputs is the inputs I said, and standard systems basically first and second order system. Then we said later on we studied non-canonical system, and we studied the characteristic of them. Like basically, if it's second order system or first order system, that's what our focus was. We get some, like we time DC gain, time constant for first order system, overshoot, settling time, rise time, peak time, all of those, right? Error, steady state error, to get all this specification. And we used algebra and root locus to place dominant closed loop pole to give desired time response. So now, if you have a desired time response, you use your controller to achieve this desired response. Your controller basically, what's it doing? Your controller basically is shifting, is relocating the poles of your system to meet to another place to meet your desired response. And how we are doing that? We are doing that, how did we find the parameter of the controller in order to shift the open loop pole to a closed loop pole location where it meet my desired response? How we did that? We did that using algebra, like system identification, as a starting point if the system is not canonical, and if canonical, then it is exactly, it meets our response. And or by using root locus, and we did little bit root locus design. So we know, like for case of gain, we can add integral, we can add zeros and poles to reshift the or reshape the root locus to pass by your desired zone. So your desired at the end closed loop poles. So then at the end it's your desired response. So you reshape your root locus. Then we did this using root locus and algebra. Root locus, it's more easy, it gives you faster response than algebra, because algebra getting to be complicated. Remember when we was talking about this PID, and when we do identification, it gets more and more complicated to know to do the system identification, right? So then root locus importance of is just make your you don't need to use algebra anymore, just use the root locus. It helps you getting the gain faster. We didn't spend too much time on root locus, but that's the idea of it. It facilitates the time. You don't need to do algebra, especially if it's higher order system. But you need to keep in mind always, you need to always keep in mind that if the system is higher order system, then all the rules that like settling time or overshoot, not exactly accurate. So as a starting point, so then you need to look to the time response and you readjust your gain iteratively to meet your exact requirement if the system is non-canonical. If it's canonical, whatever you did in root locus or algebra, you will get exactly the response that you desire. But if your system is with zeros or with higher order system like non-canonical system, then in this case you need to retune maybe your parameter a little bit by looking at the time response, the exact time response for your input, and check, did I meet really the requirement? So this, the gains that you find are a starting point. So then advantage of pole placement is that the time response can be affected directly, easiest for canonical. So here the advantage of using pole placement compared to frequency response we'll see is that you can look to the response, the time, you are seeing the time domain, so you see how the response is behaving. But in frequency response maybe we are unable to see how the system actually behaves in time domain, because that's how the system look like. It's we are dealing with time. Just it's as a human being we are function of time, right? So we analyze things based on time. So then the advantage of pole placement approach is that the time response affected directly. You can look at it, and easiest for canonical systems. Why? Because canonical system you exactly meet your desire. But if it is non-canonical, so you need to retune a little bit. But actually you're still working with time. But what's the disadvantage of the pole placement method? Whatever, if this pole placement is algebra or root locus, both we can call them pole placement, because you are by changing the gain you are moving the location of your closed loop pole to meet your desired location. So what is the disadvantage of this approach, the pole placement approach or the time domain approach? The disadvantage of it, sometimes it's difficult to determine the effect of higher order poles and zeros, effect of zeros. If you have higher order poles and zeros, it is difficult to determine it using algebra and root locus, because this is non-canonical system, and you need, as we said, we need to retune things. So then it becomes difficult too. So is there a way that permit me to determine things without retuning my parameter? This is a frequency response. So in frequency response, then able to see directly the effect of the zero or higher order system. In another word, if it's your system is non-canonical, better to work in frequency response. So then you don't do iteration. So then this is a disadvantage of pole placement approach. It's difficult to determine the effect of higher order and effect of zero. Other words, is non-canonical system. And also one important thing or one disadvantage of this method, root locus, is it's difficult also to determine how the system will respond to complex inputs. Okay, we always think if it is, and the analysis we did, if the system is only step. But what, okay, we studied one system types, what about how to predict it, especially system error and so on, if it is ramp or parabolic. But what if the system is more complex than that? So then it's difficult to determine how the system will respond to complex input. However, in frequency approach, we can predict how the system will behave for any input, for any complex input, as I told you last session. Why in frequency response we able, this is a question for you, why in frequency response we able to see the behavior of the system for any complex input? Why do you think?
I don't know.
Yeah, others? So I repeat the question. Why do you think in frequency response I'm able to see how the system it will behave for any complex input, which is not the case in pole placement method, in time domain analysis. In time domain analysis, I cannot predict. We studied the system for step input in particular. Then we can know the settling time, overshoot, all for a step input only. But if the system has complex input, I cannot predict its behavior. I cannot determine how the response will behave if I'm using time response. But I'm saying in frequency response, if I'm using frequency analysis, we're able to determine how the response will be for any complex input. Why? You remember it from last time? Nobody remember? Nobody at all? By the way, also this is not control, guys. This is your if you are taking frequency analysis in some courses, I'm not sure, systems and signals, or so. Do you know that any complex input, or do you remember from last time that any complex input we can write it as a summation of sinusoid with different frequency, like
Yes.
series, Taylor series, and so on, those kind of math. Any complex input you could represent it by summation of sinusoid with different frequencies, right?
Yes.
Right.
So if that's the case, what we are doing in frequency analysis when we was working with body plot, we are applying a sinusoid by varying frequency and looking to the output. At the end, this means so I can predict the behavior of the system at any complex input, because a complex input is a summation of sinusoid with different frequency, and that's what you are applying here. You are varying you are sweeping the frequency within a band range and studying the system within this band range. So then you can know how the system will behave, how it will respond for any type of input. So that's basically about. So now I have this input, and that's my output will look like. Basically, you have, if I apply my input, you will see you have transient and you have steady state. This is the transient section at the beginning, is any input you apply, as we was working in step, for example. You have transient maybe, and then later you have steady state. Exactly the same. When I apply a sinusoid, I have transient and I have steady state. So in our frequency analysis, we care about the steady state only. How much is the amplitude, and how much is the phase, amplitude and phase, with respect to the input, without caring about the transient response. And by the way, if you know the output and input, so you know the frequency response, you can do system identification as well, as we are doing in time domain. We know the input and the output, so we can identify what do I have inside the GS block. Alright, so the transient we don't care about in our, because it's short, and what we care about is only the steady state response. And the steady state response, always we have steady state response behaving this way if the system is stable. If your system is stable. So if we don't care about this response, but I will tell you, this is the response if you need it. If I have R sine omega t, then my output will be Y sine omega t plus phi, or phi. This is the steady state response. Y is the amplitude of my steady state response, and omega is the frequency of my steady state response. Because the system is linear, my omega is the same. Input and output have the same omega, plus a phase shift compared to the input. And what about the transient response? The transient response is governed by this equation, which is A E minus sigma t sine omega dt plus psi, if you wish, plus psi. What this mean? You have omega here, the damping frequency. So the damping frequency, which is omega d, and omega d related to omega n. So omega n, let's say it's the natural frequency of the g of s. So not your input. Here your input is omega. Don't get confused. Here your input is omega, but here omega n, okay, which is the natural frequency of this. So omega d, omega n, 1 minus zeta square. Okay, that's the omega d I'm talking about here. And phase shift compared to the system. And A is on amplitude, some amplitude E minus sigma t. With time, let's say time scale, of course. With time, you have this attenuation. The sigma, if you remember, is the attenuation. Okay, it's the settling time, related to the settling time. It's the attenuation of your curve, your envelope. Okay, so that's the sigma, if you wish. But we don't consider, we consider this part as negligible. It's like you are saying my sigma, I will consider it equal 0. So I'm neglecting the settling time.
لا يا دكتور، كمان هي على الانفينيتي لو بتصير بتروح هيدي الترانزيانت بارت لأن الإيكويشن بتصير تند تو زيرو.
Again, t equal
على
infinity.
الانفينيتي
Yeah.
الإيكويشن بتاعتها الترانزيانت هي أول واحدة لو بتصير ايكوال تو زيرو، فمشان هيك بنكلكتد أو شي هيك.
Yeah, at steady state. At steady state, we can consider steady state as infinity. But also, we consider sigma as negligible here in this case. Like, we go directly to 0 from the beginning. But yes, I agree with you. This analysis is when t tend to infinity, this term will go to 0. But why I'm saying I want to neglect sigma? So I'm saying we want to neglect sigma to tell that S equal sigma plus minus j omega d equal sigma plus minus j omega n minus 1 zeta square. So now if I want to take sigma equal 0, with sigma equal 0 and zeta equal 0, then I have plus minus j omega n. Somehow my S will be plus minus j omega n. Okay, for this system. So like to say, if I want to draw body plot, if I want to draw body plot for g of s, just replace s by g omega and change the omega frequency, you will get the steady state. So to get the steady state, to get the body plot, what we do to get the body plot is we replace s by j omega, and that's how it came, from where it came, why we need to replace s by j omega. Yeah, this is, we'll see it later, that actually when we want to draw body plot, but just now remember it, when we draw body plot, s will be replaced by j omega, and the explanation why, because basically we are interested to look at the steady state only. So here it is. So how do I draw my frequency response concept? Two primary quantities of interest that have implications for system performance are the magnitude and the angle. The magnitude, or the scaling, is y over r. You remember from last slide, I have them y and r. Okay, then y over r is actually the magnitude of your system g of s, where s equal j omega. That's how we determine j magnitude, j omega, then you vary omega, and the phase is the phase angle of j omega. And this is concept, frequency response concept, is important for designing controllers, non-canonical controllers, but even for canonical. Also, it's important, this concept, frequency response, for filters, for choosing sensors, also because the sensor have a band, frequency band. When you're working with sensor, you will see that each and every sensor has a frequency band, right? On which you should work. You should keep working only. You make sure that your signals are within the frequency band. Otherwise, you will not get the information from the sensor. So when choosing sensor, when designing mechanical systems, also we need to think about the frequency response, because you need to avoid any input that can vibrate your system too much. So you need to make sure that you have, for example, if you are designing a suspension for your car, so you need to make sure that when you're designing the spring, it is a vibration coming from the road, or the force coming from the road to the tire through the suspension. This force applied should not have a frequency equal the natural frequency of your spring, the suspension, natural frequency of the suspension. If the noise coming from the road has a frequency equal to the frequency of your suspension, then your car will vibrate a lot. So you should avoid that. When you're designing your spring for your car, you need to make sure you design it, you put the thickness for it, the length for it, whatever, at a natural frequency. Any system has a natural frequency. Omega n square, if it's second order system, for example, S2 plus 2 zeta omega n, S plus. So this omega n for the spring should be far away from the force applied from the road to your suspension. So then it's also for mechanical system, just one example, but you could think on any example that will vibrate at the natural frequency, as you saw in the PowerPoint in sometimes, just here, right?
Yes,
So at
resonance.
the natural frequency, your system will vibrate a lot. So you need to avoid the natural frequency of your system. So that's why those concepts are important, frequency analysis, for many domains, even in signal and system, filter, telecommunication, etc. Radio communication, telecommunication. Frequency response analysis, attenuation may be desired, noise. So attenuation may be desired or undesired. In general, you have attenuation, and this attenuation is maybe desired or undesired, like noise and disturbance or commanded reference input. So here what they are saying here, like that's your system, and you may amplify it or you may attenuate it. If it is a noise and disturbance, you desire to attenuate the signal. If your input is noise, if your input is disturbance, you desire to attenuate it. Okay, but it's undesired to attenuate the input, your real input. So you have controller, right, and this is your input. So the input is something, or whatever input you have, the input is something you are undesired to attenuate it. But if it is a noise on the sensor or a disturbance, alright, disturbance or noise, so this is you desire to attenuate them. And by working in frequency response, you'll be able to control those signal and to know where to attenuate, what to attenuate, what not. So amplification can destabilize a system. So here what I'm saying is, if you amplify the system too much, can destabilize a system, like if you are at resonance, for example, and then you may have a lot of amplifications and it lead to unstable system. Also, phase lag means information is delayed. That's what I mean by phase lag. If you have a lot of phase lag, that's why when you analyze two things, the amplitude and phase, why we want to extract from frequency response two things, the amplitude and phase of the signal at any given frequency. Any given frequency, including the frequency of noise, including disturbance frequency and the desired frequency. So we need to know what's desired, what's undesired to attenuate. We need to, so we be able to avoid them. We're able to avoid an amplification that can lead to destabilize the system. Also, looking to the phase. By looking to the phase, we can see the phase lag. And what we mean by that, information will be delayed if you have phase lag. So you put your input. If you have phase lag at this frequency, so you know that your information will be delayed. And this can hurt performance and also destabilize a system. So basically here I'm telling you that that's why we need to extract the phase and the amplitude, because those information are very important, okay, in control in general. You have basically three types of frequency response: the Bode plot, which we saw, and the Bode plot is the one that we will use in our analysis to design controller. Bode plot, okay. So magnitude versus frequency and phase versus frequency. In Bode plot you have two graphs, we saw them, magnitude versus frequency and phase versus frequency. But you have also other type of representation for frequency response. You have Nyquist plot, you have Nicholas chart. We will see them only now in the next slide, but we will never see them later on, okay. But it's nice to hear about them and be able to read them and analyze them. They are also used in control, but not as much as Bode plot, okay, especially for controller design. But they are used somehow, so you may find them in your research, or so they are used but less, so you should know about them. We'll see them a little bit. So Nyquist plot is basically magnitude versus phase. At the end, it's extracted from Bode plot. Nyquist, it's another representation extracted, because at the end you have magnitude and phase. But how to represent the magnitude and phase? Here you represent in two different graphs. It's good for control. Here you represent them in one graph, and you do polar representation, polar angle, polar axis, using polar axis. Nicholas chart, they use rectangular axis. So, and also magnitude versus phase, but they use rectangular axis to plot the graph. So all are magnitude and phase, but the representation is different. So that's Bode plot. So we don't want to talk about it. It's you know it now. That's the Bode plot. You have two plot, magnitude versus frequency and phase versus frequency. All right. Nyquist plot. Nyquist plot, we said they use polar angle. Polar angle. So it means if this is 0, 0, polar angle, if you remember, polar angle is rho and theta. So if I want to represent a point here, I represent it by theta and radius. Call it rho or something. So that's the polar angle. So now, if I'm here, for example, at omega equals 0, this is the input of your signal. Okay. At omega equals 0, maybe you have radius equal to approximately 1, more than 1, and a radius of 0. Then you keep omega equal 1, your output have that radius and that angle, theta, etc., etc. And you construct the Nyquist plot. So at the end, here is your point, which is r, for example. It has radius and theta, right? And it is also symmetric if it is, for example, second order system or so on, but this is not now. We don't want to go in deep on it. So as we said, it is magnitude versus phase, but in polar representation. So if you have a magnitude and you have phase, assuming that's the magnitude, and this is the phase, so the magnitude is r or rho and the phase is theta, so then that's the magnitude and that's the phase. Okay, so in each point you recording the magnitude and the phase at each frequency. At each frequency you look to the magnitude and phase and you plot it. So at the end, the magnitude represented by the radius and the phase by the angle. Good. Nicholas actually same as body plot, but so they use gain and phase, but in uh, rectangular representation. So which means, for example, also they change. For example, at omega equals 0, they look to the in x-axis the phase and in y-axis the gain, and they put them. At another omega, keep increasing omega, and each omega they record the phase and the gain. So it's basically it's body plot, but on um, one plot instead of taking it two plots. And this is what we call Nicholas. Any question regarding Nicholas and Nyquist plot? Yes?
No,
No
no.
question. Okay. This is the frequency response in general. We will look how to interpret body diagram. Up to now, we don't know how to draw body plot. As I introduced you how to draw root locus, but up to now we don't know how to draw body plot. By the way, keep attention. So maybe in the exam, if you wish to use MATLAB to draw body plot, it's easy for you. Even later on, you'll learn how to draw body plot. If I ask you a drawing for body plot or extract some information from body plot, like find the gain margin, phase margin, feel free to use MATLAB. It facilitates you, but you can use your hand calculation as well. If I'm you, of course, I use MATLAB if it's available, because it will make things easy, like faster. I'll get faster response. So you could use MATLAB to draw root locus if I ask you to draw root locus. So, but I know this is photo. It's game. So if you upload it to me, so you upload it as MATLAB, or by hand is as you wish. But you could use MATLAB. It's all right. So, how to interpret body diagram? We don't want to go into derivation. I'm sure you will look at them, you will be able to understand them. They are not difficult. You have question, happy to answer, but usually this is we don't explain. They are clear, so you can look. But here, just what I want you to is to know how to interpret body diagram. Basically, if you have a body diagram like this, then you directly tell me, yeah, before saying, in the interpretation, a body diagram, specifically the magnitude frequency plot, okay, the magnitude frequency, not the phase, can use to determine the system type and the static or error constant. So by looking to the magnitude frequency plot, you can tell me the system type, is it type 0, type 1, type 2 or more, and the static error constant. You remember Kp, Kv and Ka for system type 0, type 1 and type 2. You can find them by looking at the body diagram. For a given system, only one of the static error constants is finite, this is we know, and is also directly determines the system type. So both information can be determined by observing the low frequency. Both information, the static error, the static error and the system type, so Kp, Kv, Ki, or system type 0, type 1 and type, so type 0 Kp, this two information, type 1 Kv, this two information, or type 2 Ka, this two information, this both information can be determined by looking at the low frequency region of the body diagram, in particular magnitude frequency plot. So looking only at the low frequency. So let's go and look at the low frequency as they said to us here. Okay, I look at the low frequency. Here is the low frequency. What I see a constant. When you see a constant, directly interpreted by the system of type 0. Directly tell me, if I ask you in the exam, give you a body plot, and ask you what is the types of the system, you look to here, and directly you tell me it's a type 0 system. If I tell you why type 0, because you have horizontal here. Okay. Then, if I ask you what is Kp, equal to how much? So you tell me I can find Kp by looking to, assuming here you have 40, or assuming here you have 40 decibel. So you will tell me I can find Kp by taking 20 log Kp equal 40, if this is 40. So 20 log of Kp equal 40, so you can know the Kp for your system. Here is the derivation for demonstration, but now I'm telling you direction. So then you tell me Kp equal 10, so log Kp equal 40 over 20, 40 over 20 log 10 of 10, then Kp equal 10 to the power 40 over 20. Okay, is it clear how to determine the system type and the Kp for this particular diagram? If I give you body plot, it starts by horizontal line.
Yes, yes.
So now, if your body plot, that's how to interpret. If your body plot start by a line like this with minus 20 decibel per decade, if it has a slope of minus 20 decibel, if it has this minus 20 decibel per decade, then you tell me directly it's a system of type 1. You look to the slope, the low frequency. Remember, the low frequency just at the beginning. You don't need to. Here maybe you have I'm not sure how it is, but you have a body plot that go like this later on maybe, and later on, etc. for example. So this we don't interested. Just we interested on the low frequency. Look to for me to the low frequency. Then if it's minus 20 decibel per decade, you told me it's type 1. Then what's Kv? To find Kv, you keep your horizontal line, taking it until it cross the x-axis, the frequency axis. And you tell me in this case, the frequency that you find here, assuming it's omega 1, which is 10 radian per second, 100 radian, whatever. So the omega 1 that you find here, you tell me this is your Kv. Here is the derivation, you can look at it. But so that's how to find Kv and system type. To tell me it's 1 in case you have minus 20 decibel per decade. If you have minus 40 decibel per decade, you will tell me it's system of type. What's the type of the system if I have at the low frequency minus 40 decibel per decade? It's a system of type
Type 2.
Type 2. And so then you still need to find Ka. So how to find Ka? As we did in system of type 1, you take it and you go and to cross, you continue the line, the low frequency line, up to it cross, as in the system type 1, the frequency axis. And where it crosses the frequency axis, here is assuming its frequency equal to omega A. Okay, it crosses in a frequency equal to omega A, which is maybe 10, 100 radian per second, whatever. So this frequency, omega A, it is equal to Ka, square root of Ka. That means Ka, if I want, just omega A square. So then I find the frequency here and I take the square of it, I get Ka. So I can know the Ka and the system type of it. Knowing the system type is important when designing controllers. This is, don't forget it. Knowing the system type is important in designing controller, because so it depends on the system that you are applying. You can predict the steady state error from the table that we know. Okay, this is one interpretation for body diagram. This chapter is about interpretation of body diagram. You have another interpretation, which is the stability margin. From looking to the body plot, we can know the stability margin. And here is the definition. So for stability, gain margin and phase margin of the Bode diagram must be positive. So here I'm saying and, not or. So for stability, the gain margin and the phase margin, which we know how to find them, this gain margin and phase margin of the Bode diagram of the open loop system. So you look, I'm putting them in bold, in blood, this black. So just, and in capital letter, open loop system must be positive. Why? Because the student often so we need to shout here, we need to raise the voice. Okay, open loop system, that's my open loop system. I open it from here, Tariq, right? So from here we open the system. Yes, maybe I have here H, so then your open loop system is G times H. So you take the arrow and you open the system, then you get E from here to here, a transfer function. That's the open loop system. So for stability, gain margin and phase margin of the Bode diagram of the open loop system must be positive. So you need to draw to me the Bode diagram in the exam for the open loop system and check if the gain margin and phase margin are stable or are positive or not. Maybe I give you a trick and tell you G of S by itself the gain and phase margin are stable, but I'm putting here H. When you multiply G by H, you may find out like then the system becomes unstable. So for stability, that's what you need to look for. Gain margin, phase margin must be stable for the Bode diagram of the open loop system. Okay, two trick I want to tell. Bode diagram can be used to infer stability for a system in a unity feedback. Then I just was saying, okay, I want to give you H here. So if H means it's not unity feedback. So if I'm giving you H, you need to convert it as one time we did in the homework in one exercise, how to convert it to a unity Bode diagram. We solved it in one exercise, how to convert it to a unity diagram. So then if I'm giving you a system like that, please guys convert it to a unity feedback first, and the resultant of it use it for stability. Okay, Bode diagram can be used to infer stability for a system in unity feedback due to the variation in the system gain K. Like I have the right to write my G, then it's then at the end, even if G1 times H, so they will be G, and G is in a unity feedback form. So then you pay attention to this. So and G, I have the right to write it K n over numerator over denominator. Also, I have the right to write S time to the power n. It could be n0, so nothing here, and n could be system type. Okay, and then I keep varying K. I can vary in K and check the stability. But this is we don't vary K. We take K equal 1 and we look to the phase margin and gain margin. G must be stable. So to draw the Bode plot, Bode diagram can be used to infer stability for a system in unity feedback to the variation in the system K if these two conditions are met. I should have two conditions. In addition to the G must be unity feedback, I should have these two conditions if I want to draw the Bode plot. So maybe I give you a trick in the exam to check your understanding. I give you a G unstable. In unity feedback system like that, and unstable, you go and draw Bode plot. This doesn't work. You should not. G must be stable. If you want to infer the stability, to look to the stability of a system in unity feedback due to variation in the system gain K, then G must be stable. That's one. G must be stable. And second, G should be a minimum phase transfer function. So what is minimum phase transfer function? You know how G must be stable. This is something you can check. You check if you have no right half plane poles. If you don't have right half plane poles, you tell me the system is stable. But how to know if it is minimum phase transfer function or not? This is still didn't take. I didn't teach you how to know if it's a minimum phase transfer function, so I'm telling it to you now. That's how you need to check. G is a minimum phase transfer function if it has no zeros in the right half plane. So here then no right half plane zeros. So then I should have no right half plane poles and no right half plane zeros. Even if the right half plane poles, like a self-balanced robot, for example, or inverted pendulum, this is not necessary to lead to unstable system. You can have a system with right half plane, but at the end, if you have right half plane poles, this system we call it minimum phase transfer function, and we call it non-minimum phase transfer function. So then to be minimum phase transfer function, you should have no right half plane poles. So no right half plane poles and no right half plane zeros. If these two conditions are met and your system is a unity feedback, in this case you draw the Bode plot and you find the gain and phase margin to infer stability.